Welcome back to Bio30 Prep. In this lecture we're going to continue our discussions on the properties of matter, and we're going to be talking about the structure of matter, but more specifically the theories about how matter is made at the molecular level. By the end of this lecture you will be able to describe the past and present ideas regarding the nature of matter, describe the development of atomic theory, and when you're doing this, you're going to be outlining the changing ideas about matter through the work of Dalton, Thomson, Rutherford, and Bohr. You're also going to be able to identify the general properties of subatomic particles. Early ideas, when we take a look back into early history, the ideas of Aristotle. Normally when you start a science course, you end up with the history of science, and you almost always start with Aristotle. He was dipping his fingers in everything. He developed a theory that all matter consisted of four elements: earth, air, water, and fire. He also put together this idea that the qualities of matter were compositions of different amounts of fire and earth, air and fire, air and water. So these qualities: dryness, hotness, coldness, and moistness. Aristotle's theory had two forces: conflict and harmony. Conflict was thought to cause bad things, and harmony was thought to cause good things. Aristotle also believed that the heavens were made of a fifth superior element named ether. Now all of this sounds kind of strange to us, but his theory was accepted for almost 2,000 years. It wasn't until after the scientific revolution when true atomic theories prevailed. Now that doesn't mean there weren't earlier theories, it's just they weren't accepted because they were less popular. Democritus had the idea, or he coined the term atomos, or atom, to describe the smallest unit of matter. He believed atoms were ever moving and could be described in terms of position, shape, size, impenetrability, so things could not go through an atom. They moved through space, or he called it the void. He said qualities such as thought and sensation, atoms interacted. So he gave more than what we do. We have the idea of matter and not matter. To him, everything was matter. So he even had the concept of a soul, or described the concept of a soul by using soul atoms. He stated that physical phenomena such as state were caused by compounds of atoms. So as you put atoms together, you ended up with liquids or solids or gases, depending on what shape or what qualities the atoms had. So he would say that atoms of water were smooth and round, and therefore they were unable to hook together, which is why they remain at the liquid state at normal temperatures. Iron atoms, because iron is a solid, they must be jagged and rough so they can hook together to form some kind of solid. He also believed that atoms could not be created or perish, so kind of the idea of conservation of mass. He didn't call it that, but it's along the same lines. More similar to our current ideas, but Aristotle was more popular, so his theory was the one that got accepted. Aristotle was wonderful at arguing and winning debate. So if you were good at debating, then your ideas flourished. If you weren't so good at debating, then even if you were right, you were less likely to be believed. Kind of the same as now. It wasn't until about the early 1800s, when the first paper, John Dalton's first paper on atomic theory, appeared, and he demonstrated the usefulness of assuming that elements were composed of small units that he called atoms. And he said that atoms of any one element have the same physical and chemical properties. So this is the idea that if you have oxygen atoms, all oxygen atoms are the same in terms of physical qualities and chemical properties. Atoms of different elements have different properties. A compound is composed of atoms of specific elements with definite integral numbers of atoms. So what this is really saying is that the atoms, if we take a look at our water molecule here, this water molecule has 2 hydrogen atoms and 1 oxygen atom. And what he says is that every single water molecule is composed just the same way. So every single water molecule has exactly 2 hydrogens and exactly 1 oxygen. And this is the integral part. So an integral number, or if you want, we could say a whole number, or a counting number, in terms of the type of atoms and the number of atoms that make up a compound. He also described chemical reactions as rearrangements of atoms. None of the atoms are destroyed, and no new ones are created. So this is an extension of Lavoisier's law of conservation of mass. So the idea was what you start with is what you end up with, just a rearrangement of atoms. So Dalton's theory talked about the atom as being the smallest part of matter. Thomson, however, discovered through the use of a vacuum tube that there were smaller particles than atoms. So through his experiments in the 1890s, he found, or he identified, an electron, the smallest particle that he knew of. And basically all atoms have electrons. So the atom is no longer the smallest particle, no longer the smallest known particle. He discovered electrons, and he provided an atomic model that would explain all the known properties of atoms at that time. So what he said was that all atoms are spheres of positive charge with negative spheres embedded in them. So this is the raisin bun theory, where you have a bunch of negative charges. I prefer chocolate chip theory in my honesty, but raisin bun. So this is a sphere, and these negative charges would be your electrons. And this yellow part here is a positive charged mass. With the electrons bound on the outer surface. Now, his model wasn't correct, but it explained the current scientific evidence. So it was the simplest possible theory, so it was the one that was used. So simplest explanation at the time. And one way to look at scientific theories is that if they aren't broke, don't fix them. So it wasn't until Rutherford discovered a problem with Thomson's theory. He was shooting alpha particles through gold foil, and he basically said that if the Thomson model was right, then the alpha particles should travel straight through the atom and nothing should happen. And for the most part, that's what happened, but occasionally a alpha particle would be shot at the gold foil and it would bounce back, either straight back or deflected at a really severe angle, and that didn't make any sense. So Rutherford had to change atomic theory in order to explain this result. So he said that atoms have a nucleus, and in the nucleus are neutrons and protons. And really, he just talked about protons. So, protons are in our nucleus. And those protons are positively charged. And that's why occasionally, although not very often, those alpha particles would bounce back. Alpha particles have a positive charge. If they head directly towards something with a positive charge, those two positive charges repel each other and the alpha particle is bounced back. So Rutherford's atom did a good job of explaining what protons were and where electrons were somewhere around the outside of it, but it didn't explain their behavior very well, or it didn't explain why don't electrons crash. So electrons should crash into the nucleus. Because the nucleus is positively charged, and it's a big positive charge. The electrons around the outside are all negatively charged, so why don't they just get a crash into the nucleus that they're attracted to? So that led to the Bohr theory of the atom, and he explained how electrons can have stable orbits around the nucleus. What he said is that electrons move in orbits of fixed size and energy, and he got this from looking at as energy was released from an atom, it was always the same. It's a very brief way of putting it, but basically he looked at what kind of energy was given off when electrons lose energy, and what he found is that electrons always lose set amounts of energy. So that's how they stay in their orbitals, is because they have a set amount of energy, and they can never lose enough energy to keep them or to get them to crash into the nucleus. So the farther the orbit is from the nucleus, the higher the energy, because it needs to have more energy to stay that far away from the nucleus. Radiation occurs when electrons jump from one orbit to another, and this gives off visible light. Atoms are more stable when their outermost shell is filled up. So it turns out that atoms are less likely to react with other atoms when their outer shell is filled with electrons. So this outer shell is given a name. This is the valence shell. Now we'll be talking more about that in a couple lectures. Now there's one more theory regarding atomic model. It's the quantum mechanics model. It's the basis for modern atomic theory, so it's the basis for what people believe the atom looks like now. It's used to describe properties of matter and the particles that it's composed of. In the quantum mechanic model, atoms are composed of still a nucleus containing protons and neutrons. Protons still have a positive charge, that's important, so positive protons, neutral neutrons, and negative electrons. So protons are positive, neutrons are no charge. Around that nucleus, though, they've changed how electrons exist. So in the Bohr model, electrons exist in these set energy levels. In the quantum mechanics model, electrons exist in a cloud. So it's not so much that you can pinpoint an electron, but you can guess as to where its location is going to be based on how much energy it has. So it's a bit more complex than the Bohr model, and it's one that we're not going to be using in this course simply because it's too complex for our needs for Bio-30 prep. So what you should be getting from this lecture is that our current understanding on the nature of matter started with the work of Dalton. The nature of elements and compounds is based on the idea of the atom. So we describe matter as being composed of atoms. The Thomson model Thomson discovered the electron, so it was the beginning of subatomic particles, and these subatomic particles were negatively charged. Rutherford discovered the nucleus of an atom, and he said that the protons are in the nucleus, electrons surround the nucleus, and again, protons are positively charged, and the nucleus is extremely small compared to the size of the entire atom. Bohr arranged the electrons into energy levels, and each electron has a fixed amount of energy that can be measured in units called quanta. And that is, for us, the level of atomic theory we need to know in order to describe matter at a biology level. I will talk to you in the next lecture.